Morning, folks. This is lecture 19 on March 21st, 2023. Now, I had this in-class presentation earlier this morning, and there were about 20 people there, 25 people there. And I just wanted to let you know that there were some issues with the slides that I had on the screen, and I noted that. I told the students that I will correct those slides, and when it comes to posting it, like I'm recording right now and post it on YouTube, the corrections are going to be made. So, yep, just be aware of that fact. Now, the Uh, agenda today is mainly that item one, and what you see below it is really related to item one. So we want to discuss the orthogonality of the mode shapes, both in terms of mass orthogonality and stiffness orthogonality, and then out of that, we will be able to reach item number 4, which is decoupling the equation of motion or modal analysis. Now, all of this may sound strange to you because you haven't seen it, but I hope that you have watched lecture 18 at least to have an idea for what is involved. We're only going to be dealing with the two degree of freedom system because beyond that, everything essentially has to be done with the computer. Uh, two degree of freedom system involve 2 by 2 matrices, and anything past that, 3 degree of freedom system, 5 degree of freedom, they're all 3 by 3 matrices and 5 by 5 matrices, which are not going to be easy to manipulate manually. Now, the other thing is that there is some additional material in Inman's book where I'm skipping it, okay, and those are related to what is called the mass, what is it, the mode, I forgot the term, mode normalized, mass normalized modal mode shapes, etc. And I'm going to ignore that because it's not essential for getting to the bottom of the things. Okay, so here's the situation. The mother of all equation, namely mass matrix times the second derivative plus the stiffness matrix times the displacement equal to 0, is reduced really if we are dealing with linear dynamics to finding the natural frequencies of the vibration. So this comes from mx double dot plus kx equal to 0, where a particular form of x is selected. Okay, let's not worry about that right now. We move on. If you take this and multiply both sides of this expression by m inverse, notice that we're going to have m inverse times m, which is identity, and m inverse times k, and we get this. And this may look familiar to you because it looks like the stuff that you saw in your second year linear algebra class. It's something with a minus sign, something times I plus the matrix. This is the matrix. Now, your math teacher probably wrote this thing as uh, a minus lambda I instead of minus lambda I plus a. They probably juxtapose these things so it's that a minus lambda I times a vector u equal to 0. This was called an eigenvalue problem. Now, notice that the solution to this is the useless one that you can see here. Obviously, when u is 0, this whole thing is 0. The other one is when this matrix, if you don't want a 0 u to be a solution to this, you need to have this matrix to be singular, okay? Or the determinant of it must be 0. Now remember this. This is the stuff that you saw in your second year linear algebra class. Now, and it's fine. There's nothing wrong with it. It's just that you compare these two. There is your matrix A. Oops. There is your matrix A, and there is minus lambda I. The problem is that this matrix, the way you did it, because of multiplication by M inverse, this is no longer symmetric. Although the individual matrices M and K are symmetric, M inverse of K is not symmetric. And although for small sized matrices, we can actually go down this alley, but for large sized matrices, doing it this way is not going to be numerically possible. Okay, so we're not going to strictly do it the way your linear algebra teacher has taught you, professor has taught you, by looking at it this way. We're still going to stick to uh, the uh, the form that we have over here, instead of converting this to a minus lambda I, we're going to treat it like this. Okay. Now, there is a couple of other things you should remember from your linear algebra class, and that is when you have the two matrices and you multiply them together and you take the transpose of it, it's the product of individual transposes, but these are reversed. Okay, so B transpose first, A transpose next. And the same thing with the inverse. When you take the AB inverse, assuming that these inverses exist, the inverse of this product is inverse of the second one times the inverse of the first one. These are handy things that we're going to need. Actually, this one is particular that I just wanted to remind you about. Okay, so first of all, we're going to discuss the concept of mass and stiffness orthogonality of the modes, and we'll be patient. We're going to find out what exactly you have in mind. Now, the mass matrix that we deal with is diagonal because we are using the lumped system. But if the mass matrix is not diagonal, all of the stuff that we're going to do today is going to go through, except that you need a little bit more, care, and that is called the Cholesky decomposition. We are not looking at this, although there's a couple of pages of your Inman's book and pretty much some other textbook, well-known textbook devoted to this. But for the first course, it's not necessary to assume that the matrix is not diagonal. Okay, so here's the mother of all equations. The mother of all equations. This, you have seen it in the single degree of freedom system. If you have damping, you add to this Cx dot. But for the present discussion, because we're talking about natural frequencies, undamped natural frequencies, we are going to ignore the damping. Now, let me remind you, this is something new. Here it's M, a K, or 2 by 2 matrices. But if this was a single degree of freedom, you had seen this thing for the first 3 weeks of the course, 2 weeks of the course actually, okay? And there I went down maybe a slightly different path. I said that, oh, you know what? Why don't we assume that X is some constant, say U, times sine of omega t. Or X is some constant, say U times cosine of omega t. But you can do it in a more general way, U equal to e to the I omega t, because e to the I omega t from Euler's equation can be thought as cos omega t plus I sine omega t. But anyway, this is the only place in this course that we ever need complex numbers the way I'm presenting it. So you take this thing and you stick it in that equation. So assume that the solution like that is like that. And remember, m is 2 by 2, k is 2 by 2, x is 2 by 1. So x has two components, x1, x2. That's why I have a vector here. And that's why this is a vector, but that is, of course, a scalar. So if you differentiate this thing twice, you're going to get minus I squared omega squared t. And if I squared is minus 1, so if you take that stuff and plug it in here and divide by e to the I omega t, you're going to get that equation. The mother of all equation reduces to an algebraic equation, no derivatives in it, which is right here. Now these omegas, this omega is called natural frequency, and U is the mode shape associated with natural frequency. In the language of your linear algebra class, kind of this is a generalized eigenvalue, and this is a generalized eigenvector. But let's not worry about that. This is what we got. We have to find omega, and we have to find U. And this we did in lecture 18. I hope that you watched it. So this is a 2 degree of freedom system. There are two natural frequencies, omega 1 and omega 2. And for each one of these, there is one eigenvector or eigenmode or mode shape. And these are called U1 and U2. So U1 goes with this omega 1, and this U2 is a vector, the mode shape associated with omega 2. Okay, so here is where we're going. If you take this omega 1 and this U1 and plug it in that equation, well, it satisfies it right here. And the same thing with omega 2. If you take this omega 2 and this U2 and plug it in here, it satisfies it. So let's take this top equation and multiply on the left by U2. And let's take this second equation and multiply it on the left by U1. I really should have used unscript U here, but that's okay. So these are, because I tried to make all the script things to be my, or characters to be vectors, but anyway, I put a bar here so that you know, an arrow here so that you know these are vectors. So multiply the top one by U2, multiply the bottom one by U1 on the left. And if you do that and subtract the two equations, notice that this term will drop out because it's going to be U2 transpose K U1, U1 transpose K U2. And because K is symmetric, U1 K U2 and U2 K U1, they're the same thing because K is symmetric. Mass matrix and stiffness matrix are symmetric uh, for this purpose, okay? So these drop out, and this is going to subtract. So, and these are the same. U1 MU2 is the same as U2 MU1, okay? And that's why we can factor it out right there. We can subtract these two. You can factor it out, and you get omega 1 squared minus omega 2 squared times this. Now, written here for your convenience, if these are not the same, then this must be 0. If these two frequencies are not the same, this is 0. U2 MU1, and this should be U1 MU2. For those of you who are watching this thing, what I really meant here is U1 MU2. And same thing here. Now, because, by the way, these are 0, if you go back here, go back there, if you go back here, when you multiply it by U1, for example, this bottom equation, the one on the left side is going to be 0 because it's going to be U1 MU2. That's 0. We just showed it on the next page. So this must be 0. The moral of the story is that these mode shapes are mass orthogonal, with the caveat that this is what I meant was U1, U2, and stiffness orthogonal. Same thing with the caveat that this is bad. It should be U1, U2. Any two mode shapes for different frequencies are mass orthogonal in this sense and stiffness orthogonal in this sense. That's exactly what you need. Now, in your linear algebra class, you were told that two vectors are perpendicular if the dot product is 0, without the m, of course. Well, we are not saying this. We are saying if you stick an m in between them, or stick a k in between them, this is going to be 0. Okay, so just be aware of that fact. Now, if I had decided to follow Inman's few pages on the things that we are skipping, then something like that would have popped up too, but we're not going down that route, okay? Now, assume that the mass matrix is diagonal, otherwise you have to go and use the Cholesky decomposition, which we're not doing in this course. So, you found U1 and U2, you put it in that matrix. So the first column of this P matrix is U1 vector, 2 components. The second column of this matrix is U2 vector, 2 components. So this is U1 as a column vector, and this is U2 as a column vector. Again, bad mistake. This should be 2, 2. Might as well do it here. I can do that. Okay. Save this. And while we're there, let's clean this up too. Well, that's okay. We can do that. I can do that later. Okay, so let's go ahead here. Here's the story. Take the first mode shape, put it in the first column. Second mode shape, put it in the second column. You get two vectors like that. Each one of them is a mode shape. This is U1, this is U2, and this is called the modal matrix. Okay, it's called the modal matrix. P is the modal matrix. Now, I will leave it to you to show this. Now, for the people who are in class this morning, I actually went through this product and showed people that it is going to be a diagonal matrix 0, 0. M itself is diagonal, so you might say, oh yeah, okay, M is diagonal, what's the big deal? But K, this matrix K over here, this matrix A, stiffness matrix, was not diagonal. However, if you left multiply it by P and right multiply it by P, it becomes a matrix which is actually diagonal. So please go ahead and work this out. If you have any questions, come and see me, or go to the GA, or come to the tutorial and ask me there. Now, this M tilde is called the modal mass matrix. Remember, the P is called the modal matrix because in it we have the different modes. M tilde, which is diagonal, is called the modal mass matrix. K tilde, which is also diagonal, is called, for this 2 by 2 system, of course, you can see that, is called the modal stiffness matrix. Notice that this is a number and this is a number. This is a number and this is a number. Fine. Now, M1 tilde and M2 tilde, which is incidentally, there are these two things. These are not the same as M1 and M2. And the same thing with K1 tilde and K2 tilde, which is not a big deal. It's these two numbers. They are not the same as K1 and K2. Just be aware of that. All right, let's do an example. And this is the problem that actually was discussed in lecture 18, and I got the equation of motion for you here. This is a 2 degree of freedom system, and what we want to do is to go through these calculations, actually verify that they are mass orthogonal, the mode shapes are mass orthogonal and stiffness orthogonal. Although I did mention this thing in lecture 18, but we never talked about it, pursued it. I just said verify. So we want to look at what we have done here in the context of this example. Okay, the equation of motion in lecture 18 was derived. So very simple. Just draw the free body diagram. And for each mass, right, sum of all the forces is equal to mass times acceleration. You get this. So there is my matrix M, big matrix M, and there is the big matrix K. This is the mass matrix. This is the stiffness matrix. Notice that the mass matrix, because of the nature of lump masses that I'm considering, is diagonal, but the stiffness matrix is not. Okay, you can see that. These are not zero. All right, so let's go here, take these numbers, stick it in there. These are the mass and stiffness matrices. Stick it in there, you're going to get this. This is diagonal by, because of the lumping of the system of the problem, and this is not diagonal. You can see that. Now, the mother of all equation, you have to find this matrix and its determinant equal to 0 and solve for omega. Here it's easy. It's 2 by 2, and therefore it's going to be a quadratic equation, essentially a quadratic equation. Actually, it's going to be a fourth order equation. However, when you look at it, this is omega 4, this is omega 2, so we're dealing with a quadratic equation. So you can solve this, and you get two values, plus or minus 2, plus or minus root 2. Now, the minus ones, we're not going to worry about it. When we looked at single degree of freedom system, the first 2 weeks of the class, we never talked about negative natural frequency, okay? So there's no reason to do it here. And we're going to look at only two positive frequencies, 2 and square root of 2. And we patiently, and this is, I mean it, patiently you have to take 2, go find the eigenmode, U1, or the mode shape, and repeat it for omega equal to root 2 and find U2. But let's do omega 1 first. This is where I had some issues in the presentation this morning, okay? For some reason, I call this thing omega 2 because I think it came from somewhere in lecture 18. Although there's nothing wrong with lecture 18, it's just that I want to be consistent with what we have done in the class today. So I'm going to call this thing omega 1 equal to 2. Okay, omega, this is omega 1. I think in the presentation this morning, I called this thing to omega 2, and then I ran into the vector being, computer being U2, etc. So, and it's okay when we did in 18 because there was nothing to worry about. But here, I want to be consistent with what I've done today. Okay, so take this 2 and stick it in there and patiently find U1. Okay? There is no shortcuts around this thing. You have to do the hard work, or you have to have a program to do it for you. For okay, for 2 by 2, no problem. Right there. So I've done omega 1 equal to 2, put it in there, done the calculation, this. Notice that it looks like you have 2 equations and 2 unknowns, but actually these 2 equations are identical. One is 3 times the other one. If you multiply the bottom equation by 3, you get exactly one on the top. So you really don't have 2 equations. You have 1 equation, 2 unknowns. So we can set arbitrarily, we set U2 equal to plus 1. Could it have been something else? Yes. Would that give you a different U1? Yes. But it turns out that once you get the decoupled equations, okay, once you get your m uh, m tilde and k tilde, it doesn't matter. We'll get there. We'll get there. So here's U1. Patiently put omega 2 equal to root 2, the other root. Work out the second eigenvector, second mode shape, patiently. And once again, it looks like we have 2 equations, 2 unknowns, and that is not the case. We have 1 equation and 2 unknowns. And once again, patiently U2 equal to plus 1. Yeah, you can use something else if you want, it doesn't matter. And that's going to give you the corresponding value of U1 and this. Now, if you take these 2 and stick it into the matrix P, you're going to get your modal mass matrix P. But I just want to confirm this thing. Let's take U1 MU2. Plug it in. Do I get 0? Yes. Let's take U1 KU2. Do I get 0? Yes. Try it out. I'm not saying U1 U2 is 0. U1 dot MU2 is 0. I'm saying U1 MU2 is 0. Okay? We already talked about this. Now we want to see how is this thing going to help us to solve the equation of motion, to decouple the equation of motion. Remember, the whole reason behind finding these mode shape and the frequencies is to be able to decouple the equation of motion. Okay? That's called modal analysis. So, this matrix P, I already told you, if you take the U1 and U2, put it in the columns, the 2 columns of matrix P, you're going to get your modal matrix. Now, what it does is that, remember, the physical coordinate is x. This may be 2 translation, 2 rotation, 1 translation, 1 rotation, it doesn't matter. But the physics is behind x. But we're going to make a change of variable. We go from x, which is what we want, to some other coordinate, which is called q. These are called modal coordinates, okay? Through the matrix P, this is the change of variable. So I can write it like that, or we know that big X, or this X, not big X, this X is a vector, 2 components, so I put an arrow there. Q is a vector, 2 component, Q1 and Q2, I put an arrow there. This is meaning the same thing. Now, I took this and stuck it in that equation. So we have m p q double dot, because if you differentiate this thing twice, p is a constant, you get q double dot t, q double dot, plus k pq equal to 0. I'm going to multiply on the left by P transpose. You're going to get this. About 5 minutes ago, I told you that this is a diagonal matrix that we called it M tilde. And this is a diagonal matrix that we call it K tilde. Modal mass matrix, stiffness, modal stiffness matrix, okay? And I wrote it like this, or I said M tilde Q double dot plus K tilde Q equal to 0, which is essentially the same. But the point is that these are diagonal, okay? In the long way, in the long term, if you want to write these things in terms of, U1 and U2, it's right here. This number was that number. This number is this number. This is the first modal mass right there. This is the second modal mass. This is the first stiffness, modal stiffness, and second modal stiffness. The moral of the story is that the top equation, first row, has nothing to do with the second row. Modal mass matrix, Q double dot, plus stiffness, modal stiffness matrix, K tilde Q equal to 0. But the point is that we no longer have this. We have the corresponding things where the tildes are put on top of M and K, and the x's are no longer x's. They are these modal coordinates Q1 and Q2. Okay, this is a vector. Good. Modal mass, modal stiffness. Mass matrix, stiffness matrix. Modal mass matrix, modal stiffness matrix. Okay, completely decoupled. Have nothing to do with each other. If you want to write it in the longhand, the first row says this. There is no Q2 in it. You want to solve that? You can do it. First 2 weeks of the class. Your first differential equations class. You want to solve this? No problem. You can do it. There's no Q2. There's no Q1. Okay? These can be solved independently of each other. That's why the equation of motion are decoupled. But it has a cost. You have to know the matrix P, the modal matrix. And that is expensive in general. Let me remind you that Q had these two components, Q1 and Q2. Instead of X1 and X2, X1T and X2T, we have Q1T and Q2T. Remember that this number is just U1, which is the first mode, time mode shape, time M, time mode shape. This is a mistake. Bad mistake. This should be 2. It's better to clean it up here, things that can be done right away. Okay. Now it's good. Now it's good. Ooh, same thing here. Yes. Good. Modal mass matrix, modal stiffness matrix. In terms of matrix notation, this is M tilde, it's P transpose MP, and this is K tilde, P transpose KP. You can see why this P is so important. So let's go to the problem that we just did. Just a few minutes ago, I found the mode shapes. Remember, I put arbitrarily something equal to 1, find -1 there, and for the second frequency, I set it equal to 1 arbitrarily, find the other value. So I put them in the column. These were the mode shapes associated with omega 1, which happens to be 2 radians per second, and omega 2, which happen to be √2 radians per second. Now, go to the next page. This was the actual stiffness matrix, non-diagonal. This was the actual mass matrix, which happens to be diagonal for lumped systems. Earlier today, we did this just a minute ago, 5 minutes ago. If you find P transpose MP, it will be diagonal. P transpose KP, it will be diagonal. If you multiply that P on the left by K and multiply it on the right by P, you're going to get this. So what if instead of making these things arbitrarily equal to 1, you made it some weird number? So for example, what if we decided that this mode shape, but we're going to set its U2 equal to, instead of +1, check the video, please, back it up, minus 0.3. Well, if you put minus 0.3 here, this top number, U1, is going to be 0.1. So what I'm saying is that, remember, you arbitrarily set things equal to 1. Okay, no problem. You could have set it equal to something else. I'm saying, what if we set it equal to these two numbers for each? And then you work it out, you get a different modal mass matrix and a different modal stiffness matrix. However, look at the ratio. We're going to see. Look at the ratio of these two. Okay, look at the ratios of these two, and you'll see that they lead to the same equation. So let's see now. So with this choice, 2 times Q1 plus 8 Q1 double dot, this is multiplied by Q double dot. So 2 times Q1 double dot plus 8 times Q1 equal to 0. And for the second row, 2 times Q2 double dot plus 4 times Q2 equal to 0. And what if we did this? Well, it's going to be 0.18 Q1 double dot plus 0.72 Q1 equal to 0, and 0.072 Q2 double dot plus 1.44 Q2 equal to 0. Please write it down. This is what we get. And aren't these the same? If you multiply the top one, if you divide the top one by for example 0.9, by 0.9, if you divide what is that? Well, let me put it this way. If you multiply this thing by 0.9, wouldn't you get this? 0.18? And 0.9 times 8 is 0.72. And over here, if you multiply both sides of this by 0.36, you get this, and you get that. The moral of the story is that these will be different. These will be different, but the decoupled equation of motions will be the same. Okay? The choice of the modal mass matrix, the modal matrix P, because there was arbitrariness involved here, the choice of this was arbitrary. But irrespective of what you use, as long as they're mode shapes are not unique. That's why there is arbitrariness involved here. The decoupled equation of motion will be the same. They don't look the same, but this is a multiple of that, and this is a multiple of this. Okay? All right. Okay, let's move on to this problem. Now we want to look at exactly the same problem that we did a minute ago, except that we want to solve actually those equation of motion. We want to find out what x of t is, x1 of t is, and x2 of t is, or are, as a function of time. In order to do that, you better give me some initial conditions. So suppose that the vector x, which has x1 and x2, at time 0 is given by that. And the velocity at time 0 is this. In other words, I took this x1 block and moved it to the right by 1 millimeter. This state where it is, and just released it from that condition. This begins to oscillate back and forth. Both of them will actually. And I want to know what the solution is. What x1 of t is and x2 of t is, or are, as a function of time. Okay. So let's go ahead and decouple the equation. We already did about 20 minutes ago, the mode shapes associated with this problem. We already went through it. This was a modal matrix. The first column is your mode shape associated with the first frequency, which was 2 rad per second. This was the mode shape associated with the second frequency, which was square root of 2 rad per second. That is the change of variable. Notice that because everything is going to be written in terms of Q, but initial condition is given in terms of X, I better find out what Q of 0 is, okay? Because X of 0 is given to me. That means you can find Q of 0, okay? So to do that, all you do is to multiply both sides of this by P inverse, and you're going to get that, okay? And there's the matrix P. P inverse is this, very simple. You can just work it out. And now you're going to say, okay. First of all, the decoupled equation of motion, it's from the previous page. We already have it right there. This gave us that decoupled equation. Remember, this gave us that. Just go to the previous slides. Okay. Now, that equation was associated with this frequency, 2 rad per second, and the second one was square root of 2 rad per second. Now, in order to find the solution to this equation, you need initial conditions. Okay, initial conditions. Now, if you go back to the second week of classes, if you have this equation and the initial condition, the solution of that equation, because it has nothing to do with the second one, can be written in this form: an amplitude and a phase. And the same thing with the second one, because it has nothing to do with the first equation. An amplitude, its own amplitude, and its own phase. Now, we need initial condition. This D1 and D2 and phi1 and phi2 depended on the initial condition. Let's find the initial conditions for Q and Q dot. These were already given to us at t equal to 0. This was 1 millimeter and 0. This was 0 and 0. Okay? So if you plug in 0 here, you can see that Q of 0 is just P inverse X of 0. And Q dot of 0 is just P inverse Q dot of 0. This was 0 vector. This was the vector 1 millimeter and 0, right? You just plugged it in right there. 1 millimeter and 0. And that will give us initial condition in terms of Q1 and Q2. And for the derivative, these were the initial condition for X. You plug it in, you're going to get 0 and 0. Now, we're down to the second week of classes. You have a differential equation here. This is how the solution is going to look like. This is how the initial condition will look like. Q1 of 0 is minus 1.5. Q1 dot at 0 is 0. You better find D1 and D2 and phi1 and phi2. If there are any issues, go back to stuff from the first 3 weeks of classes. Okay, so I worked it out. This is very simple. You found Q1. Well, you find D. Just literally write these down. There are 4 equations from unknowns: D1 and phi1, D2 and phi2. These 4 equations involving D1 and phi1, D2 and phi2. These are the 4 equations. Okay, and get the D1 and D2. Solve for D1 and D2 and phi1 and phi2. 4 equations for unknowns, and you're going to get this. For those people who were in class today, a lot of these numbers were different because when it came to the omegas, I called them differently, etc. But anyway, this is all corrected. Now, we are interested in X. I don't give a hoot what Q is. I want to know how much my mass has moved. So I want to know X1 and X2. Therefore, from what we have here, which is the whole picture about Q1 and Q2, I put it back in there, back substitute, and you'll get my X. So there's your modal matrix. There's the P. There's the Q's that you found, Q1 and Q2 that you found. Just literally multiply it out. You get this. Notice that phi1 and phi2 were pi over 2, and these are signs. So I took the pi over 2 out, essentially wrote in terms of cosine. So there we are. Okay. Now we can plot these. Exponent location of the mass 1 as a function of time is here. Location of mass 2 as a function of time is here. Notice that these are all periodic. These are all sinusoidal, but involves both frequencies. Both frequencies. In general, if the initial conditions are arbitrary, you will have both frequency popping up in your solution for physical variable. Okay, now here's the second example that I want to do today. Uh, we have a vehicle modeled as a 2 degree of freedom system. This is not a single degree of freedom system model of the car, which was just bouncing up and down. Here you have bounce and there is a pitch involved. The degrees of freedom that I'm using here is displacement, vertical upward displacement of the center of mass and the counterclockwise rotation of the chassis. Okay, so if you look at it, you're replacing the actual vehicle with its half model, basically. The left side of the car, right side of the car, bundled together. So basically we have two springs, front and the rear, and then this is the chassis of the car bouncing up and down and pitching counterclockwise. Okay, good. The first thing you need to do is to write the equation of motion, and this is the kind of thing that you did in the first and second week of classes. So in order to do that, what we did, we assumed that this thing went up by x and rotated. So the amount of stretching, of this spring is not only x because the whole thing goes up, but it also rotates. It's going to be x plus b theta, small angle oscillation. B times theta is going to be that length. And this one is going to be x. The whole thing went up, but because it tilted counterclockwise, it actually reduces the shrinkage of I don't know what this thing is. This is supposed to be ground. It looks like that. Anyway, by a theta. So once you have the amount of stretching and the compression, you can write the multiplied by the appropriate stiffnesses. You can get the forces acting on this system, on that. And now we're going to write sum of all the forces in the vertical direction equal to 0, and sum of all the moments about the mass center. I'm sorry, did I say 0? No, I didn't mean that. Sum of all the forces in the vertical direction is mx double dot, m being the mass of the car, and sum of all the moments about the center of mass being j theta double dot, the kind of thing that you did in the 2 weeks of the class. Okay, this is vertical force in upward direction, mass times acceleration, forces. We take the moment about this patiently, respecting the direction of rotation positive counterclockwise according to this drawing. And so this has a negative contribution into the moment, and this has a positive contribution to the moment. Okay, it looks like that, the mother of all equations. Your m is, well, first of all, your x is vertical displacement and counterclockwise rotation. It's not always displacement, always translation, sometimes mixed. In this model is a mix. By the way, if I had used as my unknowns, degrees of freedom, the vertical deflection of the front of the car and the vertical deflection of the of the rear of the car, both of those will be deflection, and you have x1 and x2 here. But I decided not to, like I did differently. For this data, you can just plug in, find the big matrix M, it's right here, and big matrix K, which is right there. I forgot to write your K here. Please, you can add it yourself. This M, just clean this up and write your K here. And I have a feeling it's going to be K1 minus K2. Actually, I'm not sure. You can just look at this here, right there. It's going to be K1. Yeah, it's going to be K1 minus K. No, K1 plus K2 is going to be K1 plus K2. K1 plus K2, and that's why some of these things 12,000. I just literally have to go and clean this up, okay? So, yeah, I'm not going to do that. Okay, there we are. You have to find the natural frequencies. So the mother of all equation for natural frequencies is right here, minus omega squared m plus k, determinant of it equal to 0. Patiently solve for the two frequencies, right there. Patiently take omega 1, go find the first mode. In other words, this times u1 equal to 0, solve it. Notice that you don't have two equations here, you have only one. Believe me, you have only one, okay, because you did determinant equal to 0. And arbitrarily, we're going to set u2 equal to plus 1, and you're going to get u1. So this is the first mode shape. This is the mode shape associated with that frequency. Let's patiently go and do the second frequency. Okay, clean it up. Arbitrarily set u2 equal to 1, because these are not two equations. These are one equation, two unknowns, so we can do whatever you want with one of the variables. I'm going to set it equal to u2. Remember, this omega 2 we know is right there. Okay, so this is not an unknown here. And you're going to get u1. This is the second mode shape. Put them in the matrix first column, second column, right there. You're going to get the modal matrix. Patiently do P transpose PM. Believe me, it's going to be diagonal. And P transpose KP, believe me, it's going to be diagonal. But wait a minute, what are these things? This is not diagonal. But look. This is to the power of minus 12. So for all practical purposes, this is 0 and this is 0. This is 0 and this is 0. Yes. So essentially, that's what I've got. These are the modal mass matrix and modal stiffness matrix. Okay? Now, if you want to write the decoupled equation, just go ahead and work it out. I mean, this number goes here, this number goes there, Q double dot, plus this number and that number, this matrix, Q equal to 0. So these are the two equations that have been uncoupled, and patiently you can go ahead and solve it, okay? Independently of each other. Once I give you initial conditions, now I didn't give you initial conditions here because essentially it becomes the previous example. I mean, once, and the initial conditions are always coming from the inverse. I give you stuff in terms of X, you need in terms of Q, you need the Q stuff, okay? So we just, I mean, if I gave you the stuff, you can find the initial conditions from here, like that. And go ahead and look at what we did a few slides ago. And that's it. That's it for the lecture today. Yes, there's a lot of, I don't know, math. That is true. And this is why we don't do anything beyond 2 degrees of freedom system. Remember, if these were 3 by 3 matrices, and ultimately if these were 1,000 by 1,000, 10,000 by 10,000 matrices, as it happens in the finite element package, it cannot be done manually. Calculating the matrix P, in other words, finding the frequencies and finding the mode shapes, is an expensive venture. This is why when you, for example, use a finite element package such as, I don't know, the CATIA, ANSYS, Abacus, they don't go and extract all frequencies. Usually they default to 10 frequencies. But remember that these frequencies, in principle, there's infinite number of frequencies. When you idealize the problem with finite element or lump it according to what we have done here, you reduce that to a finite number of frequencies. Now, not all of them necessarily are going to contribute substantially to the I don't know, a particular behavior of the car that you may be interested in. So of all these frequencies, maybe 10 of them or 20 of them, whatever, are the ones that are going to substantially contribute to the system. Now, what we're going to do on Thursday is on the right-hand side of the mother of all equations, I put down equal to 0. What if it's not 0? What is the force acting? Okay, a force acting, and we're going to have to see. We're going to see how the decoupling is done with the force acting. We still use this modal matrix P. That's critical, and we're going to do that on Thursday. All right, folks. Good luck, and I'm sorry about this issue here. I forgot to write down the matrix K. You can go ahead and clean this up and find out what it is. It's very simple. I told you already that the matrix K, on the top left corner, you have K1 plus K2. The one next to it, in other words, first row, second column, is going to be, uh, it's going to involve A and K1. You just have to clean this up. Okay, you just have to clean it up and write it down. And A and B are going to pop up in this matrix K. Okay, A and B are going to pop up in the matrix. Okay. All right, good luck.